we have a system which is being manipulated by a controller. The controller occurs in this part of the block diagram, and this is the standard control loop. So here we have our standard feedback control loop. Everything that we are talking about when we talk about a PID controller happens inside of that GC. So in a very real way, when we design a controller, we are obtaining an expression for GC. Later, we'll be doing this in the Laplace domain. You'll see that chapter 7 takes a time domain approach, because obviously, real things do not exist in the Laplace domain by themselves. If you build something, they just exist in the time domain, right? And so if you're just thinking about how a system like this would work, it would work in the time domain, and you would be thinking in the time domain. Now, so we've got this error signal, and the transfer function, the relationship that we're always looking at, is effectively an expression for P as a function of E. That's always what we're trying to figure out. This is what a controller does. On a very high level, if we weren't doing math, the controller itself, the actual physical device, which is the controller, is effectively mapped by that gray box now. In other words, we've spoken about this a couple of times before. You have this controller. It has ports that you can plug in, perhaps a thermocouple, perhaps some other measurement equipment. Maybe it's a pressure sensor, maybe it's whatever sensor you have. That is coming in over here. Okay? So this is the measured value of that signal. The box usually will have that set point right on the front. And then inside of the box there's math. Or inside the box there's actually, in realistic terms these days, a computer chip that is running through a little program. Back in the day, and you still see some of these controllers were completely electromechanical. In other words, they would be built from components like relay, inductors, and capacitors, and resistors, right? So the kind of stuff that you did in EIR, you would be able to design a PID circuit that didn't have any, let's say, sequential logic. It would just be doing, be doing all the kind of calculations that we write down in the math. It would be doing that in circuitry. And I mentioned last week that some of the first early controllers were things like the Watt governor, which was also completely mechanical. There was not even electricity involved. Okay? All of the math that we're writing down here are just like usually where we have in CPN, we wrote down math that describes physical processes. The physical processes typically come first, and then we write down a mathematical description so that we can analyze those systems without having to interact with them all the time in physical real life. And you guys already have seen the benefit of this. I know almost nobody here is actually using their actual TC lab for most of the stuff that they're doing with the TC lab. Isn't that amazing? Right? Like that little button that you can click that says, no, I don't want to actually wait 5 minutes for that to happen. I want to click on this button and make it go 10 times faster. The only reason why that exists is because we have math that describes the action of that system. If we didn't have the math, if we only had the system, the only thing we could do would be to kick it and see what happens. Okay? And so that's the first important thing to understand, is that the physical devices precede the math. People didn't write down math and then build these devices. They built the devices. The Watt governor existed before Maxwell analyzed the stability of controllers. And so, in a very real sense, when we talk about these things, it's not something that we found. You know, these mathematical artifacts didn't come from nothing. They came from describing the action of a controller. And so think about these different kinds of ways in which controller action could be conceptualized. And I think an easy way to think about this, I advise you to get out of the habit next week or kind of sometime this week where we'll be moving from this intuitive understanding to the more mathematical understanding, but I do recommend that you think about the controller right now. Allow yourself to imagine yourself in that situation. Okay, so imagine, I think this is something that is a pretty good, widely used or widely understood example. Imagine you are trying to water the garden. So you have a garden hose and it is attached to a tap. Okay. Right. Now the problem is your buddy's on the other side, he's at the tap, you're at the garden hose, right? So you're trying to water the garden and you're trying to communicate. Maybe you're around the corner, your friend can't actually see what's happening. This, I think, how many people have had this at least or can picture this idea, right? So you've got a tap, you've got a long garden hose. The person who's manning the tap cannot actually see the end of the garden hose. And so there's a communication issue, right? There's the person on that side is going to have to give commands to the person at the tap to get the right amount of water to go out. Right. And so this is actually a control loop. It's useful here in this particular case to think about it this way because of how automatically most of us are able to do control in cases that are not quite as contrived as this. When I say contrived here is you could say much the same thing about things about standing under a shower and trying to control the temperature, except that because you're doing all of it yourself, it's not as easy to understand the conscious steps that you do. Right? Because it's like, well, how do you do that? Well, I just do it, right? Like I turn the tap until the temperature is right. That's how I do it, right? But here, you're forced to kind of address this idea of there's a person kind of telling the other person what to do, and they have to make these decisions. They have to say, no, that's too much. No, that's too little. So let's imagine, so let's talk about this, the initial part of that, right? No water is flowing. Person around the corner says, okay, open up. They've got some kind of target in mind. They know how much water they want to come out. Perhaps this is not a known system for everybody, so it's always a bit of a unknown thing, exactly how much you have to open that tap to get the amount of flow that you want. You want to get it exactly right. You don't want to like blast it everywhere. You don't want to have it drip out. So you say, okay, go, open the tap. Now person, so let's say we've got person W doing the water and person T doing the tap, right? Tamara and Walter. Okay, so Tamara is the tap person and Walter is the water person. Okay, so Tamara opens the tap. In this loop, the various different parts, let's just label these parts, right? So when we think about it, actually, this feedback loop over here, the part that actually is saying, I'm observing that, and I'm making some kind of a decision, or I'm putting that into my algorithm and making some kind of decision about what to do. That's all happening over here. So Walter is actually also the controller. Right? And the system is obviously the hose, right? So that's the system. Although from the point of view of the controller, actually, Walter is saying commands, and Tamara is hearing those commands. And so actually there's this layer here, which is actually from the commands from the controller to what actually happens in the system, which is perhaps the actual turning of the tap. There's a thing in there which we'll call now the actuator. Okay, so this would be effectively the valve if you were talking about a normal chemical engineering control system. The controller doesn't actively immediately change the valve, right? Like it gives commands to the valve. It can change a pressure signal, for instance. The valve itself also has dynamics. It changes. It doesn't immediately move to a new position. It accepts the commands and then tries to follow them. Right, so tomorrow is the actuator. Right, that's the whole of everything that goes from her ears all the way through to the tap. Right, that's the actuator. The system is taking that valve fraction and converting that to a flow rate. Okay, so the system is the everything that goes from how open the valve is all the way back. Okay, now we can start thinking about strategies that Walter could use to get the flow that he wants. Now remember, it's easier to think about this when you imagine the hose is very long and there's some kind of a delay in the flow. So Walter says open. Tomorrow opens a certain amount, right? Does that make a certain kind of sense? You wouldn't just, when somebody says open, just immediately say, cool, I'm just going to start opening. I'm going to keep turning until they say no, right? You'd usually say, well, I'm going to turn it three turns and see what happens, right? So that turn it 3 turns and see what happens is effectively a proportional change. Now, to make this analogy a little bit nicer, you can kind of imagine that Walter has some kind of a volume or urgency to how he's asking for this, right? So he could be saying, okay, cool, and then he's like, more, I want more now, right? So he's raising his volume. That's effectively giving an urgency, and you can imagine tomorrow opening the valve more in response to that urgency that the controller is asking for this. Now, if you think about it, actually, Walter is choosing that volume based on the difference between his expectations and what's actually happening. Does that make sense? So you wouldn't be shouting for more if it's already doing basically what you want, right? Like you only shout for more if there's not enough. Or, equivalently, you could suddenly be pushed back on your feet by this massive spray of water that's coming out, and then you can perhaps change the sign of your urgency and start shouting for tomorrow to stop. If she's just doing that in that moment, every time you ask for some particular urgency, she's got some particular value or location of the tap. She is acting proportionally. Right? So you can imagine that the error for a proportional controller, it's only the error that determines the urgency. And when you think about it in that way, think about this picture now, and imagine the timelines. Imagine if Walter just has the strategy, or Walter has the strategy of saying, I'm going to shout louder the further away I am from my desired amount. And I'm going to shout less hard or less loudly the closer I am to my target. You can imagine that there's some place at which there's no remaining action being taken. Okay, so you can imagine that if you shout really loud at the beginning, as the water starts coming out, and as the system starts actually getting to where you want it to go, you're going to start shouting less loudly. Okay? And what that will do is, as you shout less loudly, tomorrow is going to start actually closing that valve, because she started open. You are reducing your volume. It doesn't seem so urgent anymore. So she's like, ooh, maybe I got to it wasn't that urgent, immediate. I'm just going to scooch it down a little bit. It looks like maybe it wasn't as bad as I thought. Maybe it wasn't needing to be as open as I thought. Now, the consequence of this is that there will be a volume, there will be a non-zero or some shouting volume that will allow the water flow to be an acceptable distance away from the set point. Because there'll be a point at which I'm kind of just modulating I'm not shouting very hard. She's not like changing anything because she's like, oh, okay, that sounds about like this amount. And we reach equilibrium, steady state, not being at the top. Now you've got to kind of picture, a lot of you are thinking now, and this is a natural thing to think, but no person would do that because they would keep going until the shouting stopped completely. Right? They wouldn't just like run out of steam. But here I'm asking you to kind of imagine that Tomorrow has the strategy, right? The strategy is, I'm just going to use, every volume has a space on my tap. This is proportional control, and this is the problem with proportional control, is this equilibrium away from zero error. Right? Where I'm still saying things. Right? I'm still shouting, or I'm still maybe murmuring, but I'm not murmuring quite loud enough for the tap to get to the place where it needs to go to get zero error. So, what would a real person do? A real person would have communication and say something like, are we there yet? Like, is it there yet? Right? And while Walter is saying, so while there is an error, while Walter is saying, oh, not quite there yet, it's very close but not quite there, a real person would start turning the tap and keep turning it slowly until the shouting stopped completely. Now, this, and that would take out, let's say this is flow, and that would take out that last little bit of error. And so this is actually, let me just say, sorry, shouting volume is like this, and eventually Walter will completely stop shouting. So adding integral action, adding this extra bit that says it's not enough to have a single tap position that maps to an error. Because eventually we'll reach equilibrium at some non-zero error. Having just this logic, and this logic, forget about integrals, right? Just think about the logic of saying, I want to move the tap. I want to turn the tap and keep turning it until such a time that there is no error left. Now, when you start talking about it in that way, remember, if the tap position is a single fixed idea, the rate at which I turn, a tap is conceptually an integrator. Right? The position of the tap integrates the rate at which I turn the tap. And so you can say, I think most people have the integrating action, in the sense that while that guy is shouting, I'm going to keep opening the tap. If he says it's too low, I'm going to keep opening it. What does that mean? I'm turning the rate. Right? I'm translating the speed of his shouting to the rate at which I'm opening the tap, which means I'm integrating. The position of the tap is actually the integral of the shouting. As if I turn fast when the shouting is loud and I turn slow when the shouting is quiet, the position of the tap is the integral of the rate. Right? And so actually, a lot of us by instinct will do this integral kind of thing, where we'll take our inputs and we'll try and do something. Let's say you're driving. But even this happens with just navigating, right? So you move something, you pull something, and you maybe initially you think it's not very, very heavy. So you pull at some certain amount. And then it doesn't move. So what do? You don't just like say, oh, you know, I pulled at that amount and it didn't move. You pull harder, right? And you keep pulling harder until it moves. So there's a lot of these kind of things where you are actually adding on over time because it hasn't done what you want yet. You are adding action. You're taking larger action, not because the error has changed, but because the error hasn't changed for a while. Okay? And so let's think about the difference now, right? So proportional action can happen immediately. That's the benefit. Proportional action is the fastest way of doing things. And most of us will have some kind of initial thing that we do. If you're trying to lift an object, there's an initial, you have to have a guess, right? Like you can't just, nobody starts out with like 0 weight and then like just slowly, oh, okay, it's not lifting yet. No, it's still not lifting. Oh, yes, there it comes. Like this just doesn't happen, right? You go, you take this book, you lift it, and it's only we get caught out, right? Like if it's an above average density book, you've had that feeling where, whoa, okay, well, that was heavier than I thought. You've had the opposite feeling as well, where you try and lift an empty box that you think is full of bricks or whatever, and you're like really bracing yourself, and you push, okay, geez, that was a lot lighter than I thought. So that proportional idea is I have some kind of idea of how big my action should be just immediately, without any feedback, just in that moment, I do what I need to do. Then, if it doesn't work, if I strain at that heavy box with my initial force and it wasn't enough, I can make that decision and I can go over into integrating action. Now, in real life, it's a lot easier to build devices that do those things both at the same time, right? You can just say, well, this thing just has those things added together. And this is really how these controllers are implemented. So you can say, in most cases, the math that maps to this is that the action is going to be whatever the basic action is, whatever the normal output is, plus some factor times the error. Well, let's just say, I'm going to write this out separately. Some factor times the error plus another factor, which usually we write like this, times the integral of the error. And so this thing over here, right, or not actually on the shouting volume, on the error, that surface under the error, that's this integral, right? And so the longer we stay away from set point, the bigger that integral will become. And there will always be a point, eventually, integrals work this way. If the integral is positive, eventually, it doesn't matter how big the proportional gain is, eventually that integral will be larger and will take over from the proportional action. And one way of thinking about tau I is that tau I is the amount of time that it takes for the proportional action and the integral action to have the same magnitude. So if I've given a unity error, so if the error is 1, and this is where these things come in, these open loop curves, that if I set E equal to 1, remember I'm just doing a step response, so it's not in the closed loop, I'll see this characteristic curve, right? And you can say, well, this action is due to proportional plus integral, and that action is due to proportional only, because at that point the integral is still 0. So at the moment when the set point, or at the moment when the error went up, immediately the error is 1, but immediately at that moment in time, the integral of the error is still 0, right? Because that's how integrals work. And so you can kind of imagine that this time here, where the proportional and the integral action have the same magnitude, that's effectively as long as tau I is. That's the time associated with tau I. Yes? It's not a, it is a, so this is a very important question. It's not explicitly said, but you can imagine that you have different imaginings of how this integral would be implemented. I think you're kind of thinking ahead. If you say, obviously it's not just from the beginning of time, the answer is actually, in most cases, it is just from the beginning of time. But the beginning of time for a controller starts when it turns on. Right? So remember, this controller, you turn it on, and at that moment, error is 0. At that moment, it starts with a 0 integral, and then it goes from there. And most of the time, most controllers don't have a reset button. They don't have something that you can say, okay, make the error 0 again. What you can obviously do is you can turn it into manual and then back onto auto again, and that'll typically, it's like turning it off and on again. But in realistic terms, there were, and there still are, many mechanical integrating controllers. So things that integrate mechanically are things like this tap that I just spoke about, right? So that tap is integrating the rate at which it's turning. So in other words, a typical garden tap, right? It's got a thread. And so when you turn the tap, this thing moves up and down. And so if you think about it, that's like an integrating system by itself. If you were to describe the relationship between the rate at which I turn the tap and the position of the tap, that's an integral, right? The position integrates the rate at which I turn. It translates, you can think of that tap or a screw as a device that turns that rotational motion into linear motion, right? So this is what screws do. So there are thousands of ways of actually calculating an integral mechanically. So you can have like a worm screw, so you can have like early calculating devices would have something like a worm screw like this, and you turn that worm screw at a particular rate, and the position of that little nubbin would integrate the rate at which you turn. And so you can build a mechanical integrator. It's pretty cool. You can Google for them. Like, if you ever played with Meccano when you were young, like I built mechanical integrators, and Lisa drew things like that, drew cool things on, like with Meccano. I'm not seeing that land. Meccano is like steel Lego. Right, so anyway, very, very cool stuff, but you can Google it. There are people who build integrators, and so an integrator is a device that has a pen, and you take a curve on a graph, and it's got mechanical linkages and stuff, and you take you trace a curve, and the machine then traces the integral of that curve, right, on another piece of paper. And so this is how people would integrate curves before computers. So it's like a mechanical integrator. And you can build a mechanical differentiator as well, but they're a lot harder to build. But most of them will have one of these. Another thing that you're familiar with, like a bath, right? Like a bath integrates, the bath level integrates the flow rate. And that's useful because pneumatic controllers would have little bellows. So if you think about a concertina, right? If you blow air into a concertina or into one of those little party things, have you seen those little extending party whistles? So that integrates, you can think the position of that little party whistle. If I blow in here, this position will show the integral of the amount of breath that I've blown into that whistle, right? And so this is how mechanical integrating devices were implemented. The reason why I'm off on this mechanical kick, it has everything to do with resetting the integral, and it has everything to do with understanding this other thing about the integral, which is that it can wind up. Okay, so you may have come across this during the reading, this idea of integral wind up. hopefully with this mechanical analogy, it's a lot easier to understand why they call it wind up in the first place and what exactly it means. So think about our tap situation again, right? So imagine Walter's been shouting for a while, and Tamara's just been opening that tap. At some point, most of the taps that I've worked with have this thing where you open it all the way, no more water comes out, but you can still turn it maybe like another turn. Just nothing happens, right? And so so she's turning. Remember, she can't see that the water has stopped getting more. It's just the same. Maybe it's not what he wants. He's like, I need more water, and she's turning, turning, turning. At some point, obviously, she hits the limit of the controlled variable, right? So she hits that limit. But think about it now. If there's some time gone by, and he starts saying, no, it's too much, make it less. She now starts closing the tap, but nothing happens, right? Because she's opened up, now she has wound up the tap. In other words, she's wound it past where it's actually been able to have any action. Now the controller version of this is that if you had some kind of a mechanical system like this, it could be that you have, you've extended your bellows further than the manipulated variable, actually the mapping can go open. So you keep turning, you open it even more, nothing happens after a certain point. And so in terms of your action, what you're seeing is this is kind of what you asked for, and this is actually what you get, right? So you're at the limit, and the controller still keeps integrating because the error still isn't zero. Still turning, still increasing the error integral. At some point, eventually the system comes around, and at this point, so here we will say the controller is wound up. So for this entire time, the controller is, well, actually, it's still going up, but it's winding up now because it's increasing the integral without increasing the action. At this point, it is actually starting to go down. But nothing happens because it's still above the active limit of the controller. We start winding down, and at some point over here, that's when we see for the first time actual reduction in the controller output. And there are a couple of different strategies. Digital controllers are typically anti-wind-up controllers. And so they will detect that we are trying to go down and just go down immediately as soon as we can. And it won't maintain that integral. There are two common strategies to do this. The one is to stop integrating as soon as the controller hits a limit. The other is to use what is called the velocity form of the discrete control algorithm. But analog controllers are typically position form controllers. You'll see that a little bit later in the reading. And they suffer from wind-up. But the idea of wind-up isn't limited to controllers. It can also happen to manipulated variables. Anything that has some kind of an integral and a band beyond which there's no further effect. Also recall that wind-up is a non-linear effect, right? So anytime you have stuff like limits like this, it has a non-linear effect because there's this sharp change in the equations that describe the system. Remember, we're relying on the idea that we've approximated all of our controllers like beautifully smoothly. And unfortunately, that is, in this case, not true. So wind-up is a very undesirable effect, and it's a consequence of the mechanics of building controllers in the most intuitive, simple way that you can. Okay, now I hope that everybody now has a better understanding. I will be posting this on, I've